So we'll start off then with this background of bone mechanobiology. And here, really, I love this quote from Dennis Carter, which was one of the more fundamental papers that was done on the mechanical loading and load history of bone. And so I'll just take a little bit of time to reiterate this. So he states the elaborate and mechanically efficient designs that exist in all animal skeletons on an ultrastructural, microstructural, and to some extent the organ system level are not directly a result of natural selection. And some of Dennis's work really started to explore the nature-nurture debate about how important were is the DNA versus the mechanical loads on influencing the skeleton. And he goes on to say, rather, they are to a great extent the end products of the algorithms by which mechanical energy influences growth and form. And so from here on in, this really sets the scene for some of the work that's gone on, particularly in the area of bone, in the field of biomechanics and here mechanobiology, to really understand how do the mechanical forces regulate the tissues of the body with specific interest to the musculoskeletal system. So here we have a CT scan of a femur, and this is an image courtesy of the Melbourne Femur Collection in Victoria, Australia. And the two parts of the bone that we are interested in are both the spongy or trabecular bone, sometimes called cancellous. The compact cortical bone is around the outside, the dense bone that you see here, typically down the shaft of the femur. And if you look in finer detail and kind of zoom into this, the trabecular structure, as Wolff kind of predicted hundreds of years ago, was aligned somehow to the mechanical stresses of the bone. So the stress alignment then can potentially alter the distribution and shape of these trabecular struts that make up that spongy bone. And if you look at the cortical bone, it has this very dense arrangement of cellular network, and the cells within bone are called osteocytes, and we can see them as these little dark points here. And these round circular structures that you see here in this dense cortical bone is called an osteon. And it's at this level that we see changes going on when the bone is loaded, and we see that the cells within this network, these osteocytes, these are the mechanically sensitive cells that then trigger changes to bone. So to go any further here, we really need to have some kind of understanding of the processes involved in both establishing new bone, but also then in changing this bone or remodeling. So those are the real processes that we'll discuss. But it's also interesting to have a quick look at a cross-section of this bone. So these are mid-shaft cross-sections of the femur. And here we can see then the difference between the bone across a group of similarly aged individuals. These are, again, from the Melbourne Femur Collection. So these individuals are between 78 and 80 years of age, so similar in age, but you see a vast difference in the quality of the bone. So across the top, you're seeing men, and at the bottom, you see women. On the left-hand side, you see some nice dense thickness here of the cortical bone, nice and thick. As you progressively go to the right-hand side, you see thinning of that cortical bone. You also see the porosity changes, so the density of that bone changes. And we know down the bottom right here that women are potentially more susceptible to some of these changes as they become potentially osteoporotic. So this is really poor quality bone where you're seeing much more holes and porosity present. So it really begs the question of these individuals, you know, they're the same age, but why is it that we see such a large variability in this cortical bone, both in the density and the structure? And this is really where we need to understand these two processes that are going on. And these two processes are bone modeling and bone remodeling. So they kind of sound the same. What do we mean, and what's the difference between them? Well, bone modeling is the formation of new bone, and this is the formation of bone that we see during growth and development. And of course, this happens around epiphyseal plates. So we have a diagram here showing the cartilage that's part of the epiphyseal plate, as well as the cartilage that's at the surface of the joint. The difference then with remodeling is the adaptation and regulation of the existing bone. And you can think of this as the shape changes that can go on with the bone. Now, these shape changes can occur during the growing skeleton, but they can also occur during the adult skeleton when our bone is matured. So both of these processes are regulated by mechanical loading. And we know this to be true. We've known this for some time. There has been a lot of work, particularly on bone, to try and understand how these processes actually work and the mechanophysiology by which these processes work. And it's worth us kind of diving a little bit deeper too, to understand how bone actually remodels, because it's going to help us later on when we try and understand how do we recover from a bone fatigue injury. So here we have the two parts of the bone that we've mentioned already. So we've got this trabecular bone in the blue kind of here. And these trabecular bone have cells that kind of line the outside of those struts, those trabeculae. And during this process, we have activity from cells which kind of resorb the bone. These are osteoclasts. And then there's a new bone that's laid down, which is called an osteoblast. And this process then is a continual process around the struts. And as I said before, these struts can kind of align themselves to the mechanical loads or the loading history, essentially, that you see in the bone. And here we have the cortical bone. Now, this is a little bit different. The way this remodels is through what's called a cutting cone. And this is kind of a diagram of this in process. And we have the same type of cells. So the osteoclasts are kind of burrowing away inside the bone here. And then they're followed by the osteoblasts that are laying down new bone. And so this cutting cone is nicely seen in this SEM image here. It's a relief image of bone at very high resolution. And you can see this nice formation here of this basic multicellular unit, this cutting cone here. Now, this process, if you're thinking about how long this takes, it takes around 200 days for the cutting cone to then be fully matured. So that's actually cutting through and laying down new bone. So within 200 days, this process can occur. It's a little bit less in trabecular bone, about 150 days. And what that means is that after a period of around 2 years, the total surface of that trabecular bone is remodeled. So you can imagine there's some sort of load history across time, which then dictates the structure of both the trabecular bone as well as the cortical bone. And so this is where it gets a little interesting as well, because we start to then unravel how bone actually changes and the mechanics that are involved in that. And we typically think of these bone cells, these are the osteocytes, as the ones that are sensing the changes in the mechanical environment. And they respond mostly to strain, so deformations, and also micro damage. So it's also a bit of a hot topic still, in that the biological and mechanotransductive pathways that underlie this mechanism are still unclear. So there's still a little bit that we don't know. There's some really interesting work that shows that these cells, these osteocytes, like most cells in the body, have a primary cilia, and that cilia sticks out and it's kind of mechanically sensitive. It can respond to fluid flow. So in the case of cortical bone, where you don't expect a lot of strain, you're not expecting the bone to change a lot, these primary cilia can sense changes in the fluid that's within the Haversian canals and within the bone. And there's also a lot of work looking at the integrins and the parts of the cell that attach the cell bodies to the underlying structure, and they can be mechanically sensitive as well. So this is kind of an area still of exploration. But nonetheless, we're quite comfortable with the idea that mechanical loads influence the bone. And indeed, Harold Frost, for over 20 years now, has kind of established this idea of what he referred to as a mechanostat. So this is just like a thermostat, something that regulates temperature, but in this case, this is some sort of regulation of bone. And the regulation here is just basically saying that along the x-axis, we have some sort of cumulative stimulus, and we know the stimulus to be some sort of strain, so some sort of tension or change and deformation of those cells of the bone. And the response here is to change. And the change in bone that we see has initially been identified as a change in mass, but more recently, the term strength is kind of being used here. And I'll get to this in a little bit in terms of why we use strength maybe instead of mass. But essentially, to orient you to what's going on here, we have some sort of stimulus along this x-axis. Now, down the bottom, we also have some thresholds that identify the different stages of modeling or micro damage that might occur in the bone. So we have this area, sometimes it's referred to a lazy zone, where it says the bone receives some sort of load and it's quite happy. It's not going to add any additional bone, and it's not going to resorb bone. And it's important to identify that, it costs energy for the body to maintain bone. All of those little cutting cones and osteocytes, osteoblast activity cost energy to the body. So the body really wants to stay somewhat in a bit of homeostasis. If you supply too much load, let's call it a supraphysiological load, a load that the bone is not really used to seeing, you can indicate then and see some change and adaptation of the bone. And this is where we can see some remodeling occur. We have maybe a threshold of micro damage, after which you see an increase in the bone that's laid down. And likewise, if you go the other direction and you reduce the stimulus to the bone, and the classic studies that have shown this are bed rest studies. It's well known, of course, in astronauts who experience zero gravity, that without load, you get a rapid deterioration in the strength of the bone. So the mass goes down, the porosity can increase, and you get reduction in strength. And indeed, actually, this is far more deleterious to the body than going up this end of the curve, which we know there's kind of a break here that the bone can withstand thousands upon thousands of loads before it gets to ultimate failure or fracture over here. So this is kind of interesting from the standpoint of it's giving us the foundation knowledge of how bone is laid down and how bone is adapted to its mechanical environment. So one question that kind of arose here is from this work is, can we understand what kind of stimulus really is applied to bone to predict changes in the density of the bone? So for this, I'm going to refer to some work from Rob Whalen that he did with Dennis Carter back in the 1980s. And some people may be aware of this work, and it became known as a daily load stimulus, which has been used by ourselves in the IMU STEP kind of philosophy of what we're trying to do to understand bone injury and cumulative loads. But the other thing, just of note, you might be wondering why I've got this picture of this kind of funky looking treadmill down here. Well, this is one of the first real prototypes of the AlterG treadmill. So Rob Whalen was working for NASA at the time, and he designed this treadmill that had a hard case around it. And the idea is that you could take that into zero gravity, you could take that into space, you could depressurize this chamber, and it would suck you down onto the ground and simulate, if you like, some type of gravitational load that you get here on Earth. And it was Rob's son, actually, Sean, who kind of liked the idea, because this was kind of set up in his garage at the time. and said, well, why don't we do the opposite and try and pressurize the chamber and push someone off the ground so that they can run it at zero gravity. And that was the birth of Alter G, of course, which is the interesting treadmill. We'll discuss that in a little bit more detail as well. That was just kind of a little side note. But what's going on with this daily load stimulus here? And the idea is that we know that bone responds to these cumulative loading events, the load history, what's going on during every day. The bone experiences all different types of loads. And we also recognize that the bone responds to the magnitude of each loading event. And indeed, it responds more to the magnitude than it does the total number of cycles. And so in this equation here, I'll just walk you through what's going on. We have two key terms here. N is the number of cycles that you might expect throughout the day. And the stress term here is the type of load that's experienced by the bone. So this could be ultimately the strain that's placed on that tissue. What's really important here is to understand that there's an exponent here. There's this term, this M thing. Now this term says that the stress here that's applied to the bone is actually more important than the number of cycles. And so what Rob Whalen actually did here with the study is he tried to predict, with some basic knowledge and understanding of the loads on the skeleton, he tried to predict what kind of influence different activity levels would have on the density of bone. And he was looking particularly at the calcaneus here, so the heel bone, and he was looking at different activity levels from someone who is very active to someone who is perhaps a sedentary person. And it turns out that this exponent fits experimental data really well if it's between, say, 2 and 4. So what that means, the stress is to the power of 2 or 4 times more important than the number of cycles. And this is actually, the form of this equation is actually very similar to the form of models that look at fatigue damage. So a life cycle of damage that accumulates in tissues, and it's been shown to fit experimental data to biological tissues rather well. And so this kind of makes sense then, that this form as a daily load stimulus is a reasonably good characterization of the changes in adaptation that occur in bone, because we know those changes in adaptation are related to the micro damage that occurs in the bone. So those of you who are astute in the audience might note that I've been kind of interchanging a few terms here in terms of the changes and adaptations that occur in terms of density, mass, and strength. And so it's important really to understand, what actually determines the strength of bone. And the strength of bone is a little bit complex here, because it's a combination of all of these things. So if you think of strength as being the resistance to being either squashed, we call this compression, or being pulled, this is tension, or a resistance to bending and twisting, so we'll call that torsion, then bone mass is important, but where the bone is located is actually more important. And so what I mean here, if we go back to our example, is the cross-sectional area of the bone and the thickness of the cortex, because this dictates how much resistance there will be to, say, these bending moments, which are really important for our long bones, our load-bearing bones, which undergo large bending forces. And then when we're thinking about dense bone, we're thinking there's more mass. So clearly on this side here, we've got a bone that has more mass than this osteoporotic bone, which has lots of holes in it. And so this diagram nicely kind of represents the size and shape bone has. So here we've got some examples of, let's say, these bone structures. This structure here is solid. It has, let's say, a mass of 1. Same mass over here, but now we've actually got a kind of a hollow structure, and so the diameter is increased of this structure. And over here, we've got a larger diameter again, and we've doubled the mass. So what's going on here when you look at the strength, the tensile and compressive strength, so that's if you just push or pull on these different structures, you can see that with the same mass, you need the same force essentially to either squash the bone or pull it apart. When we double the mass, we need 2 times the force, or the strength of this bone is doubled. But when you look at the bending and torsional strength, for the same mass, you have more than 2 times the resistance to bending and torsion. And look what happens here when now we increase the mass, but we also increase the diameter, you get a 4.5-fold increase in its strength. So this is really important. The shape of the bone and of course the thickness of the cortex plays a role here in maintaining the mass or density of that bone as well. And it turns out during growth and development, before the skeleton is mature, this is where we see the biggest changes in the diameter of our long bones. So this is really important public health message for our children, because they really need to be physically active during growth and development, so they experience a large magnitude of load to encourage that bone to grow in size, because these types of size changes stay with us for the rest of our lives. Okay, so what are the most important mechanical loads that cause bone remodeling? Because there's been a little bit of debate in the literature, I guess, around this idea that the muscle forces are critically important compared to the loads that you experience, which we call kind of gravitational loads, which are just, you know, the loads against gravity, if you like. And it turns out that is definitely the case. The muscle forces dominate the type of contact forces you get at joints. They dominate loading applied directly to the skeleton as well. And of course, we know that the muscle forces in utero, so still while we're a growing infant inside the womb, those muscle forces are critically important to the development and growth of our bones. But what's also really important to note is that the bending moments, once we start walking and standing up, the moments that are applied with bending, coupled with those muscle forces, are really are very strong. And those bending moments are really what cause the compressive and tensile and torsional forces that you see in the center of the long bones, which is why the shaft of the long bones has a very thick cortex and is made predominantly of cortical bone. Now, I just want to highlight some results from a recent study from Joe Hamill and his team, who have looked at trabecular bone in the calcaneus of runners. And although it's a little bit tricky to see here, I can kind of zoom in on this. What we're seeing is a relationship of the thickness of the trabecula in the calcaneus in relation, this is a cohort of runners, and you can see as the running distance increases of this cohort, we can see these people over here typically perform more running than people over here. There's some sort of positive relationship, which you might, you know, find that's not so surprising. The runners that do more running have slightly more dense bone than these do. And what's kind of also interesting to note is that these group of people up here are forefoot strikers, and these people down here are rear foot strikers. Now, it could be that their forefoot strike is actually leading to greater stresses in the calcaneus due to the muscle forces and the tension in the Achilles tendon. But there's a confounding factor here, right? Because these people are also running further. The other interesting thing they showed is the relationship between that trabecular thickness and the number of years spent running. And again, there's somewhat of a positive relationship here, which you might expect. The longer period of time you've spent running, the more opportunity there's been to lay down new bone and for the trabecula to be thicker. And the last thing, which I find, of course, very interesting here, is the age at onset of running. So at what age did you actually start running? And here we see there's a slight negative relationship, meaning if you started running much earlier in your life, so between the ages of, say, 12 and 20, there's a much greater chance that you have thicker trabecula, as opposed to someone in their mid-30s. And sorry if there's a few people out there in the audience who are in their 30s and decide to be marathon runners, but your trabecular thickness is unlikely to be well adapted to that activity. So there's kind of an interesting study there that's kind of highlighting these strains and the effect they have on the structure of the bone.